Okay, we're going to finish Chapter 7, Part 2, Newtonian gravitation and Kepler's laws. First of all, let's talk about Newtonian gravitation. Isaac Newton, who was a physicist and mathematician in the 17th century, postulated what gravity is. Basically, if you have two masses, two bodies in space, there is a gravitational force of attraction at a distance. And he formulated basically this equation right here. And we'll get more into what this means. But it uses the inverse square law, and that basically has something to do with the square of the distance. And he formulated this equation which can calculate the force between the two objects. The second theory of gravity is Einstein's theory. It is concerning the curvature of space and stating that mass can curve space or bend space, and also bends space and time when light travels around planets or stars. Actually, the light actually bends, and this curvature causes gravitation. And this is a formula that he came up with. We don't really need to use this, the general theory in this course at this level, but just be aware of it. Okay, so Newtonian gravity was derived in the 17th century by Isaac Newton, and it is still valid today. We use it to put spacecraft into space and satellites, and it works very well. So this is where we can define his equation a little bit more elegantly by saying that the force between two objects is proportionate to the product of the two masses and times the inverse square of the distance between them. So here we have the force of gravity is proportionate of the two masses, the product of two masses, times the inverse square distance. And so we have something like this. Actually, this distance is from the center of the moon and the earth, if we are using them, proportionate to the mathematical relationship and developed experimentally to a constant called g. So he knew that there was something, this force was proportionate to this equation here, but it was missing a constant. This constant is called g, or big G. And it is known as the universal gravitational constant, which is pretty much the whole universe. This is true at any and all mass that he considered throughout the universe. It's not a local constant, it is a universal constant. Okay, and the constant is equal to 6.67 times 10 to the negative 11th. These are the units. They're just there so they cancel out because this is a constant. Okay, so let's go ahead and now place the g into the equation. And this is magnitude. Of course, force is a vector, and so is r. Let's look at an example. Find the force on the moon caused by the Earth's gravitational field. Okay, so since the Earth is much larger than the Moon, the gravity field exerted on the Earth from the Moon is much weaker. So we need to find our data. Now you can look in your textbooks in the back, there's appendix that generally gives you all the information on the Moon and the Earth, and I think some of the planets. So we can just plug these numbers in to this equation up here. And we find that the force of attraction between the Moon and the Earth is 1.99 times 10 to the 20 newtons. Let's move on to now the acceleration of gravity of a planet. What is acceleration? Well, that is our g, okay? It's unique to moons, planets, stars, and such. It's a local constant, unlike g, which is a universal constant. So if we apply the second law, to Newton's gravitational equation, and you know the second law is ma, and ma is equal to force, and so we have this expression here, and then we can cancel out the m's, and we get the gravitational acceleration equation where this a would be g. So let's plug everything in, and we get 9.8 meters per second squared. And this is true for any planet or moon that you do. You can figure out the acceleration of gravity of that planet or moon. In this case, r is the radius of the Earth. Okay, let's look at a problem and just demonstrates vectors. Find the magnitude of force and the direction. So we have the sun and Earth both have a gravitational force on the moon, and we want to find out the direction of that force and what is that force. Okay, so the magnitude of the force, and this is, we're going to divide this into the x and the y components. Between the Earth and the moon is our x component, and we get 1.99 times 10 to the 20th newtons. And for our y, it is the mass between the sun and the moon. And we plug those values in, and we get 4.35 times 10 to the 20th newtons. Now we just need to find the magnitude, which is the the square root of the sum of squares, which comes out to our resultant force on the moon is 4.77 times 10 to the 20th. And of course, to find the angle, we'll use the inverse tangent. Plug those values in, and we get 65.4 degrees. Okay, so that 65.4 degrees is actually going to be from the x-axis here. So we can see this is the general pull. It's mostly towards the sun, even though the sun is much further away from the moon than the Earth is. It still does not pull directly. Okay, let's look at gravitational potential energy. Now, this is not the same as our potential energy for gravity. It is a potential energy, and as we know, the conservation of energy states that kinetic energy, the change in kinetic energy, plus the change in potential energy must be equal to 0. So, our potential energy equation, mgr, we're going to substitute h for r, and we're going to equate this to this equation right here. Now all we did is This part right here is Newton's gravitational force equation. We know that force times displacement is always equal to energy, and so we come up with this expression right here. So with this, we can calculate the potential energy of, say, a satellite that's orbiting the Earth. We have to remember, though, that this R is from the center of the Earth to the center of the satellite. So R is equal to h, which would be the altitude above the surface of the Earth, plus the radius of the Earth. And h we could designate as the altitude of the satellite if we needed to find the altitude. So let's look at an example. We have a 1,000-kilogram satellite that's orbiting Earth at an altitude of 3 times 10 to the 6 meters from the surface of the Earth. Find the potential energy at this location. Okay. So let's break down what our R is. Our R is an altitude and the radius of the Earth. Plug those in so we can find what our R is. And now that we have that, we can plug everything else in: the mass of the Earth, the satellite, and the 9.38 times 10 to the 6 meters. And we get a potential energy of 4.25 times 10 to the 9th. Now, this would be correct whether you have a negative sign here or plus. Let's look at another example. A 2,000-kilogram satellite is orbiting the moon at an altitude of 5.5 times 10 to the meters. Find the potential energy at that location. Find the force of gravity on the satellite due to the moon's gravity, and calculate the acceleration of gravity on the moon, and how many times stronger is the Earth than the moon in this case. Okay, so we have the mass of the moon, which is given in the back of the book, and we have the distance, the radius of the moon. And we can take that and we can add that radius to the altitude that we're told the satellite is at, and we get an R value of this, which we can use in our equation. Okay, and so we plug everything in and we get the potential energy. So let's continue with B. B was to find the force of gravity between the planet, the moon, and the satellite. And then we have the R, the distance between the center of the moon and the center of the satellite, 2.29 times 10 to the 6 meters, and we get a force of 1,870 newtons. And then C is to find the acceleration of gravity on the moon, which we need the mass of the moon and the radius squared times g. And so we do that and we get 1.62 meters per second squared. Now you note that the Earth is 9.8, so the acceleration of gravity on the moon is very, very low. It's about 1/6, or we have 6 times more gravity, acceleration of gravity here on Earth. Let's look at escape velocity and what that is. Escape velocity is the amount of velocity a mass must have to escape the planet's gravitational field. It's directly related to energy, specifically kinetic and potential. So the amount of energy, kinetic energy in this case, has to be required for the rocket to actually go into orbit. If it's not, it just falls back to Earth in a parabolic curve, just like projectile motion. So the path of the projectile is the same parabolic trajectory. However, if it reaches a high enough speed, when it does fall back, it will miss Earth. Okay, and so this speed, whatever the speed is, has to be maintained and reached for it to be sent into space. So how do we calculate this? Well, if we take the conservation of energy, kinetic energy plus potential energy, and in this case, the kinetic energy would be the KE, and the potential energy that we calculated before, we take these two equations right here and solve for the velocity. Okay, and so we get this expression right here, and this is telling us that the square root of 2 times g times the mass of, it could be the mass of the Earth, it could be the mass of the Moon, the mass of Mars, and the radius, whatever the radius is of a planet, the Earth or the Moon too. We could calculate the escape velocity, the amount of velocity or energy a rocket needs to have, or a space vehicle, to actually escape Earth's gravitational field and to make it into space, into an orbit. So let's find the Earth's escape velocity in meters per second, and also let's find it in miles per hour. Okay, so we use our escape velocity equation and plug everything in, and we get the escape velocity on Earth for a rocket is 11,100 meters per second. And so just so we can understand and compare how fast that is, it works out to about 25,000 miles per hour. So when a shuttle or a rocket is launched, it must reach this 25,000 miles per hour and able to itself to actually escape the Earth's gravitational field and go into orbit. Now let's move on to Kepler's laws. There's actually 3 laws. The first law says each planet moves in an ellipse with the sun at one focus. The second is a line connecting a planet and the sun sweeps out equal areas and equal times. And then the one that we are going to be majorly concerned with in this part is the third law. For all planets, the orbital period is squared divided by the semi-major axis cubed is constant. You have a semi-major active when you have an elliptical orbit. There's 2 foci. And so this is a general equation here where the P is the period, and that is the time it takes for the planet to go around, say, example, the sun, or the Earth around the sun. This period would be equal to 365 days. This is equal to A in this case, which is actually the distance. Let's just say, using Earth as an example, your sun is the distance of the Earth from the sun cubed. So let's go back and talk about the first law. We have the 2 foci, one here and one over here. The sun is at 1, it could be anything. Then we have the planet that is going to be orbiting around the sun. Perihelion is where the satellite or the planet is the closest to the sun in this example, and aphelion is where it is the furthest. So the first law states that all planets that travel around the sun travel in some type of elliptical orbit. And the second is where the areas that are at where you have perihelion and where you have aphelion. So aphelion is here, perihelion here. At perihelion, if we take an area right here and this area, these areas are both equal areas. Okay, so the satellite moves out in equal areas. However, A to B has a time, and D and C has a time. Both of these times are equal. The time it takes to go from A to B is the same time it takes to go to C to D. Okay, if that's the case, then the velocity is going to be much higher and faster at A to B than C to D. And this is basically what the second law states. So, for example, a comet which orbits the sun, some of these comets are way out past Pluto in what we call the Kuiper belt, and they are moving very slow when they're out there. So that's why some of them have a period of 75, 100, or 200 years. They move very slow. Once they get closer to the sun, they start moving faster. And they go around the sun, and then they go back out to deep space again, and we don't see them again for a very long time. So Kepler's third law is the one that we are going to be working with. So the third law states that the period and the distance the planet has from the sun is a mathematical relationship. We can derive this equation by using centripetal and gravitational force equation. Okay, so going back to the period, capital T represents the period of a planet, which is in seconds. It's the time it takes to make one complete orbit around the sun. In our case, that's a year, so that is a period. While in orbit, the planet travels at a velocity which is a function of its distance and period of its relationship to the sun. So what does that mean? Well, we can find this by equating centripetal and gravitational force equation. Here we have our centripetal force equation, and here we have our gravitational equation. Okay, they are equal because when an object is rotating, don't forget there is a force, a centripetal force to the center. And this would make sense for the gravitational force, which actually gravity is doing the same thing. As an object is going around, it usually wants to spiral down into the main planet it's orbiting. However, there's many other factors that prevents it from actually crashing. But our satellites that we do put up in space, their orbits deteriorate, and they do come crashing down to Earth once in a while. But if they get the right amount of energy, or they have some internal energy function, they can stay in orbit indefinitely. The moon, in this case, which is also affected by the gravitation of the sun, actually is getting closer to the Earth. I think 1 inch every year or so. I might be wrong about that, but it is moving closer. But anyways, these two equations, we can equate those, and we can use this to find Kepler's law. Okay, so let's look at the derivation. We're going to, we know that this velocity, which is a velocity around a circumference, okay, and it has a period. 1 revolution, 2 pi r, a period. This is the way to find that constant velocity that a planet's moving. Now, actually, if it's in a perfect circle, we would have constant velocity, but since we have elliptical orbits, that velocity is changing. As I said, when it gets closer to the, like say the Earth gets closer to the sun, it starts traveling much faster, and then the further away from the sun, it starts moving slower. But in general, our average period and velocity can be found by using this equation. The next thing we want to do, where we want to get a v square, because we're going to use that in the centripetal force equation. So we're going to square both sides of the equation. And when we do, we get this right here. And we're going to substitute this v squared into our centripetal force equation. And when we do that, we get this equation right here. Okay, and we get this right here. This into intermediate algebraic equation, and then we get what we're looking for is this right here. So we have the period squared is equal to 4 pi squared divided by the universal gravitational constant, in this case the mass of the sun. So this center part right here is actually what we call the Kepler's constant. In this case, it is the constant of the sun. Anything orbiting the sun would follow this equation. So we can take the center of this 4 pi squared divided by g and the mass of the sun, and we can just put a k to represent that part of the equation. And so we get Kepler's third law. And this is for the sun. Now this k, if we have in the case of the Earth-Moon system, we would have a k of e. Something orbiting the Earth would be a different constant than the sun. Okay, so let's look at an example using Kepler's third law. Find the mass of the Earth. The Moon's orbital distance is this. Okay, so the period of the Moon's orbit is approximately 27.3 days. So we need to put things into seconds. Okay, so we have a period of the Moon's orbit around the Earth, sidereal period, which means we look at the period it takes around as a reference from looking from space, not from the surface of the Earth, is 27.3 days, and we need to change everything into seconds. So we do that. Okay, and then we have our Kepler's third law with k of e, which is of the Earth. Okay, and then we describe what k is. K is the center right here. And then we solve for the mass of the Earth. Okay. Plug in the values. Okay. And we get the mass of the Earth of 6.14 times 10 to the 24th kilograms. Not exactly the number you would find in the back of your book, but pretty close. The number you'd find in the back of your book is 5.98 times 10 to the 24th kilograms. We got 6.14 times 10 to the 24 kilograms. So we're off about 2.7%, but that's close enough. We have to have error for our calculators. Okay, so let's look at another thing. A concept is calculating a satellite's altitude. So when a known satellite's data is known in our system, we can determine a satellite's speed and altitude if we know its period. So there is a relationship between the satellite's altitude, its period, and its distance. Also, we can calculate the velocity, because the velocity, depending on the altitude of the satellite, could be different. So what we need to do is that we need to look at other satellites. If we compare a satellite that has been launched into space, then we have another satellite that we can use to compare proportionately. That's the moon's period and distance. So, for example, Kepler's constant for the Earth-Moon system is this equation right here, 9.89 times 10 to the minus 14th. So that is the constant, Kepler's constants for Earth, but we don't really need to use this, okay? There is a relationship, and it is a ratio, that this K of E is equal to the moon and a satellite, okay? Of course, we have period squared over distance cubed. It's equal to the same thing. So we eliminate this process, at least for calculating satellites' altitude. Okay, so let's show how we do this. Find the altitude of a 2,000 kilogram satellite orbiting Earth in 48 hours. Also find the velocity of the satellite in orbit and its kinetic energy. So we have all these variables. We're going to convert the period of the moon into seconds. The satellite, S for satellite, into seconds, 2 for its period, and then R of the moon is 3.84 times 10 to the 8th. This would be the radius of the moon. Okay, and we're going to use this equation right here. Now we need to solve for R of S, the satellite's R. That's the distance from the middle of the Earth to the distance of the middle of the satellite. Satellites are not very big, but anyways, it's always from the middle or the center of the Earth that R of S is. Okay, so all we got to do now is solve for the cube root of R, which is this expression right here. Okay, so now we can plug in our values. We do the cube root on this, and we have an R of S equal to 6.72 times 10 to the 7 meters. This is the distance the satellite is from the center of the Earth. But we want to find the altitude. Okay. So we have this relationship that the R of S is equal to the radius of the Earth plus the radius, or the distance actually, or the altitude from the surface of the Earth. We need to find altitude. So if we look here, we have RV, the center, the radius of the Earth, and then we have the altitude, which both of these are equal to R of S. So plugging in the values that we know, and then we get the altitude that the satellite is at. So for the period of the satellite, it actually dictates the distance it is away from the Earth. Find the velocity and kinetic energy. We're going to do that. We're going to use this equation here, V equals 2 pi R, R of S. Make sure that you use R of S in this equation, not R, not the altitude, and also the period of the satellite. Okay, we have these values here. Plug those into the equation, and we get our velocity. The satellite is moving at that altitude and that period. So the altitude, the period, and velocity are all connected. There. And then lastly, to find the kinetic energy, we can just use the kinetic energy equation, plug our values in, and we get the kinetic energy of the satellite while it's traveling at a certain velocity. Let's look at another example. Find the altitude of a 10,000 kilogram satellite orbiting Earth in 24 hours. So we have its period, 24 hours. We have its mass, and we want to find the altitude. Also find its velocity and kinetic energy. Okay, again, we use this equation, this ratio. M stands for moon, S stands for satellite. Here's our values that we can figure out. We must change everything into seconds and meters. And plug them into our equation. And we get an RS of 4.24 times 10 to the 7th. Okay, but that's not our answer yet because we need to find the altitude. And the altitude is this right here. We can find it by taking R of S minus the radius of the Earth, and we get the altitude of 3.60 times 10 to the 7 meters. So what about the velocity? Well, the velocity, we can use 2 pi R of S divided by the period of the satellite. Okay, and that gives us our 3,079 meters per second. And then kinetic energy, we can find by using the kinetic energy equation. That gives us 4.74 times 10 to the 10th joules. Okay, and so that ends chapter 7, part 2. It's basically on gravity, Newton's laws of gravity, and Kepler's third law.